Welcome everybody to this webinar. We're covering in this webinar an introduction to chipIgnite. So welcoming people who have not experienced or tried or maybe new to the solution. And in this webinar, we're going to talk a little bit about kind of what is chipIgnite, and then I'm going to hand it over to Matt Ben on the call. He's going to walk through a specific example of how to actually use chipIgnite to implement a design and submit it for tape-out fabrication through Efabless. Okay, so again, if you have questions, please use the Q&A facility button to ask those, and we'll be pausing or taking some of those questions as we go. In addition, we're gonna also cover at the very end a quick update and preview on a new version of our OpenLane, the OpenLane tool called OpenLane version 2.0. It's going to be covered by Don on the team here as well. So look forward to that. So with that, I'll go ahead and get started. A little bit around what chipIgnite is. So chipIgnite is a solution for providing an alternate path to develop custom silicon. That silicon can be used for a number of different use cases to support kind of maybe testing or proving an idea that you have or a concept, or it could be used to accelerate or implement new functionality or capability within a product that you want to bring to the marketplace. chipIgnite provides kind of an alternate path addressing a number of different challenges historically to implement custom silicon, both in terms of just the costs associated with that, as well as the access to technology, and also simplifying kind of the knowledge and expertise required to implement custom silicon successfully. The solution is available, is very low cost and affordable. We accomplish this through aggregating multiple projects together into one fabrication run, and we're able to offer a basic level of prototyping for under $10,000 for you to get started. The way this works is you leverage a pre-existing chip called Caravel. So this is kind of a pre-built, pre-designed SoC where you can take your custom design, your custom circuitry, and integrate that and implement that inside of Caravel to get to a kind of a custom design and custom part for your own with your own design implemented. So this is kind of showing an example here, right? So on the very left is the kind of our frame or Caravel. That Caravel frame provides kind of all the power and infrastructure required for a chip. It also provides kind of an SoC based on RISC-V core built on the bottom. And then what you do is you basically will provide us a design in the form of a GDS layout that meets the criteria for integrating that within that Caravel design. And then by submitting that through the Efabless platform, we have an automatic flow that integrates that, verifies that complete final layout, and then we submit that for fabrication to the foundry. So overall, we have a kind of overall simplified process. We provide kind of everything you need to deliver and complete that solution kind of end to end, including access to tools. So if you have access to commercial tools, you're able to use. You can absolutely use those to implement your design. If you don't have access to tools, we also provide access. We also provide access to tools through a set of open source tools for implementing designs, both for digital and analog. Those, we're going to talk a little more about those tools kind of in the webinar as we go forward. But you have access to kind of download those tools, as well as download all the technology and PDK files you need to implement the design. You follow a kind of a fairly kind of a process and flow that we'll describe to implement your GDS. That, as I mentioned before, that all gets integrated and then submitted to the foundry, where we aggregate your project with other projects, up to 40 other projects, into a fabrication run. We get those once we get your wafers back. We have a pre-designed packaging solution that allows you to get your parts back kind of in already packaged into a QFN package, and then we assemble those onto a daughter card where you and provide you kind of the test board and tools for testing and evaluating your project and your design. So part of making this simplified and easy is we provide you that kind of that pre-built SoC platform, pre-designed platform called Caravel. Again, this is a little bit more information around what that looks like. But essentially, as I mentioned before, it includes a pad frame that's already been pre-designed and defined for you. It has predefined set of IOs and power and ground settings. It also includes an SoC in the bottom portion of this chip that includes a RISC-V processor, memory, and a set of kind of basic peripherals. It provides the ability to integrate, that SoC extends a number of interfaces out to this user project area that you can integrate with for your specific design if you need it or you choose to. It includes a wishbone bus and a set of logic analyzer probes, as well as some interfaces to clock and IRQ and some other functions and reset as well. There are other versions of this Caravel for people who want to do more advanced designs, where we have a version that supports specifically analog designs where you need access to high-speed I/O or signal characteristics that aren't supported by the general purpose IOs that are available here in the standard Caravel chip. There's also an open frame version of this design as well, which removes the management SoC and provides kind of the full area for designing your project if you want to implement your own SoC in place of the one provided here. All right, as I mentioned, there's a suite of one of the ways we kind of simplify and enable people to get started with this is we provide access to open source tools to do either both for digital or analog design. There's a fairly robust suite of tools available, which you can learn more about by visiting the Efabless website and checking some of the resource links provided there. One of the most significant of those that we're going to talk about is OpenLane. OpenLane is an automated kind of guided compiler, if you will, for going from RTL to GDS. And it provides kind of a guided process, an automated and guided process to enable you to do that successfully without requiring a lot of detailed knowledge. So you provide your design in an RTL or like in Verilog as an example, using Verilog as a modeling language. We provide some examples of test benches and things of how to actually verify the functionality for your design. And then by using that along with some configuration files that we provide you with examples of how to use that, you basically use the compiler, the OpenLane tool to generate your design, and you can do that in an automated fashion without a lot of interaction or expertise required to get to kind of successful GDS at the end. Okay, so I think with that kind of quick overview on chipIgnite, I'm going to turn things over to Matt to walk through an example.
Thanks, Jeff. We had one question come up that you're well suited to answer, which is 100 quantity QFN the only option now for chipIgnite?
Yeah, so we do have, in addition to, for prototyping, the basic standard offering is 100 QFN parts. We also offer options for bare die for people who need access to just bare die for their design. And if you have some other requirement kind of beyond that in terms of either the number of parts or something else, feel free to reach out to us and we can talk through with what's possibly available. But the standard options that we have today include QFN packaged parts based on a predefined package design or bare die.
So the 300 WL CSP is not an option anymore?
That's not currently an option that we provide today.
Okay, cool, answered. Okay, so I'm going to take over from Jeff then. and I'm going to take you through using OpenLane and Caravel user project to build a simple demo and submit it onto a shuttle. And most of this is available here on our website, Get Started. So we've got a number of short videos here that go through each of these steps in turn. So that's all pre-recorded. But it's also sometimes useful to see it all end to end. And also we're going to have the option for you to ask questions as we go. So I'm going to play this video that I've pre-recorded, which hopefully is going to be easily visible. And we're starting off with the templating the repository. So go to Caravel user projects and create a template. And that takes a little moment. And then you need to clone that. So after you've made the template, that's kind of copied the whole thing. And I'm going to be showing this in VS Code. This is the preferred way that we show now. So once that has been cloned, then we're going to run a command called make setup. And that basically installs all the open source tools and the PDK that you need to continue. So Dawn and Jeff, if I miss anything or you want to jump in, just feel free to interrupt. So then you just got to change into that directory and then run make setup. And I sped up this footage here. Takes about, I don't know, 5 or 6 minutes these days to get everything done. So that's installing a bunch of sub repositories for Caravel. That's the SoC Jeff mentioned. There you go. See it installing Litex Vexrisk 5. Vexrisk is the name of the CPU that's in the SoC. And then we install as dependencies OpenLane and the PDK. And you can see the PDK being installed there. And that also sets up, and then here you see on the left-hand side, looking inside the dependencies. So if you don't set OpenLane root, some environment variables, it just goes all inside your local directory. So you need to watch out for that. And that's like about 6 GB of files, so you can quickly run out of space. If you're running multiple projects, you might want to share PDKs. But if you're running just one project, it's good to just put it all in dependencies. Keeps it all in one place.
Probably good to note too, the example that Matt's walking through is installing tools kind of on a local Linux desktop. I think this is Ubuntu in this case, right? But there are some instructions for if you're trying to utilize, if you want to utilize a Mac or a Windows laptop as well. Yeah,
Windows subsystem for Linux works pretty well, and with Mac probably recommended Parallels or VM. So then this is the RTL we're going to use, timer tutorial, which is also from the Efabless GitHub repository. So I'm just cloning that locally, so I have all the files, and then I'll be showing you where they all get copied. So there we go. We've got part 1, and it's already got set up with some Verilog, and there's the RTL. So I'm not going to spend much time looking at the RTL or what this example actually does. We're just going to be looking at integrating it. So one question is, does make setup also install the analog tools? And the answer to that is no, it doesn't. You do get NetGen and Magic as part of the Docker, but you kind of need to have a slightly different setup for analog stuff. This presentation is all on the digital side of things. So here we've got the module definition for the timer. So just passing in the clock, the reset, and the I/O. And what I'm going to do is just copy these files into the Caravel user project Verilog. So we've got the same kind of setup here. Yusuf is asking, will the presentation be shared? Yes, it will be. And yeah, we'll share the link to the GitHub repository. Maybe someone can do that. Tim or Jeff, you could paste in a link. Okay, so I'm just copying all that RTL into the correct place. So that it's inside Verilog, you've got RTL directory, and then you've also got DV for digital verification. So copy the Verilog over now. And we also need these includes. So I'm just going to be focusing on the RTL includes. So that's useful for simulation. But there's also an automatic setup for doing gate level verification. And then the last thing we need is the OpenLane configuration. So I'll take the user project timer directory and copy that over into the Caravel user project OpenLane directory. So now I've got that in there. Christian's asking about the final price. No, it doesn't depend on resource utilization. It's just a flat $9,000, nearly $10,000 for 100 chips with the 10 square millimeters.
Yeah, so the die area is fixed, the die frame, everything is fixed on this solution in order to streamline kind of the whole time and cost for prototyping. But it's a fixed price. The only changes is if you want the bare die, there's some incremental cost for bare die. There's incremental costs also for ReRAM in the future as well. So we do support ReRAM as an option.
Yeah. And if you want to do something much more small, then you can check out Tiny Tapeout, which basically divides that 10 square millimeters into 500 tiny projects. So what we're seeing on here on the screen share at the moment is the configuration file, which is a JSON file. So it's worth taking a look at that, and that's like the setup. If I just scroll back a little bit in the here, we've got to tell it where the Verilog files are, what the design name is, what we're expecting the clock period, and things like that. A lot of the other stuff you can leave to be the defaults. Lewis is asking which Linux distro is recommended. Ubuntu 22, I would say. Manuel is asking about Tiny Tapeout. Just search for Tiny Tapeout on Google or go to efabless.com/Tiny Tapeout. Okay, so now we're ready to just run this with OpenLane. So if you missed that, that was me typing in make timer project. And I've sped up this footage. It doesn't take too long because it's pretty small design. There's about 40 steps involved. If you remember this slide that Jeff showed earlier, there's like this flow chart. And you can see for each of these steps, we're getting a little log message.
So I just posted the links both for the videos that Matt's kind of showing you some of them for implementation, but also there's a set of videos for the timer tutorial as well that actually gets into more around the design part of it, implementing your design and integrating into the various interfaces provided by Caravel, including like Wishbone Bus and Logic Analyzer, etc., and the IOs.
Okay, so to take a couple of these other questions, will the next processor for Caravel be supported by Litex? If so, what will be the requirements?
Will the next processor for Caravel be supported by
next generation Caravel? Mohammed Shalan could answer that.
Is Mohammed Shalan on the call?
Yeah. Sorry, I was muted. Yes. So basically, for next generation Caravel, eventually we're gonna basically use different CPU for the management SoC, which is not one of the Litex supported CPUs, but it's still RISC-V. Like more information about this CPU and basically what benefits it adds to the management SoC basically will be shared very soon when we announce basically a new version of Caravel.
Thanks. Then we've got a couple of questions. Do I have to declare both input and output even though I'm only using the pin as an output, for example? We'll cover that in a bit. And is it possible to merge a custom PDK into the OpenLane? I'm guessing that means can you use a different PDK with OpenLane? It is possible. It's quite a lot of work to do. The easiest thing is to use Sky 130 or GF 180. They both work well. But you also need to think about, are you intending to manufacture? Because if so, then the only option at the moment is Sky 130. Okay, so we'll continue with this. So that's the OpenLane run. And that works by having a make file inside the Caravel user project. So that repository we templated has a make file that knows how to run OpenLane. And now we're using Klayout to just take a look at the GDS that we've ended up here. So it's a long, thin one. And we've done it that way, long and thin, so that it fits right up against the left side, because it's a very small design, fits right up against the left side, uses the pins on the left side. And then just the connection to the bottom, the wishbone clock and the wishbone reset is extremely short path. So that makes all the timing stuff easier. Luke Vasallo asked, does OpenLane support analog I/O? Yes, it does. All the pins do support analog, but they're bandwidth limited to about 50 megahertz. I think maybe Tim's answering some of these as well, are you? Yeah, okay.
Yes, I am.
Right, good. Okay, and what I'm doing in Klayout here is just turning on off some of the decap cells and turning off the text, so you can more easily see how empty this design is. Really, there's just these standard cells at the bottom. There we go. And one reason for doing it like this is because it makes the timing easier, because OpenLane can do all the timing calculation and the buffering to those pins, and then we just abut it right up against the pad frame. Pietro is asking about the schematic view. The schematic view is the Verilog, so I just invite you to check out the Verilog if you're interested in that, because it's not an analog design. It's done with RTL.
Well, Yosis does provide a schematic view.
Yes.
I'm not sure if it's easy to get in OpenLane.
No. You just see all the standard cells, which if it's beyond like 10 standard cells, it gets very, very difficult to see what's going on. And tiny tapeout is only on Sky 130A, so we're not supporting ReRAM at the moment. Okay, so now we've got this new GDS, and you can see on VS Code as well, the dots on the left side are showing where things have changed. So there's changes in the def, GDS, left, lib, all these, where we've got this new file used for user project timer. Now we need to build that inside the user project wrapper is what it's called. And the way we're going to do that is we're editing the user project wrapper JSON file to switch over from user project example and change all the instances of user project example to be user project timer. So that's what's going on now. So I'm just changing all these instances. I'm not used to using VS Code, so I should be editing this in the top window, but I just reflexively do it in Vim.
It is a pretty inspired choice to just use Vim inside VS Code.
Inside the terminal of VS Code, yeah. So
Yeah.
forgive my VS Code skills. I just use it for these demos and haven't got used to it for daily use. There you go. I remembered. I'm on top of it again. The other file we've got to edit is the macro config. So where is this macro going to go? And I'm just going to copy what we used for the demo. So 1515, bottom left-hand corner. So with those two files updated, we've already got the hardened other files. I think now we can just run make user project wrapper. Oh no, we also need to instantiate it inside the user project wrapper Verilog. So we're going to switch this over. Oh, it's already there, user project timer. So back in the terminal, that went past too quickly, but I wrote make user project wrapper. So that kicks off OpenLane again. But now instead of the example project, it's using the new project that I'm integrating now, the timer. Also fast forwarding this.
And we did a previous webinar just talking about the different integration options and models, and this is one of them. But
Yeah, you want to drop a link to that?
Yeah, if you want more information, I encourage you to check that out.
I always want more information, Jeff. Okay, so we can see here, just opened the final hardened file. So you can tell that this is the final one because we've got that pad frame, not the pad frame, the power rings around the left-hand side. It's still not integrated into the pad frame. That actually happens on the Efabless platform. The thing that we need to submit is this. So it's the power rings and this 10 square millimeters in the middle. And now our design is there on the left-hand side. So I'm just inspecting this with K-Layout, checking the power distribution network, checking that the pins are wired up correctly. And that all looks good. So the next thing to do is the user defined. So this is coming back to the question we had earlier about inputs and outputs. The simplest way to get the IO set up is to set the user defines. So they're and you also have to set this, otherwise the pre-check will fail. So they're defaulted to GPIO mode invalid. And we need to set, I'm going to change these last 10 because the example output is a LED 7-segment display with 4 digits. So I need to change all these, at least the last 10 to be user standard output. And I'm going to set all the unused ones to be management mode input. So that means that they're accessible from the RISC-V processor. But these last ones here need to be user mode. So yeah, I think there's a better way to do it in VS Code. I don't think I had the Vim plugin installed at this point. User standard output for 27 to 37. It's got those 7 digits and the digit enables. So it's 11 pins in total. And that means that when the chip powers up, these will be the default modes for all the pins. If you make a mistake here, it's not the end of the world because you can run some firmware, but then you definitely need to have flash on the board that can set up the GPIOs how you want. So the next thing we're going to look at is the simulation. So because I mean, if you're used to FPGAs or whatever, or computer programming, then one of the nice things about that is you get the results straight away. Basically, it's much easier. I think of it like writing software is like toasting a piece of bread. You know, you have to wait for a minute, but then it pops up and it's tasty toast. But making an ASIC is more like baking a loaf of bread. You know, you got to really put a lot of work in at the beginning, and then you got to put it in the oven for a long time before you get the tasty bread. So you really got to make sure that you've measured everything out correctly and you're following the instructions. So part of the way of doing that with ASIC is on the verification side of things. And often people spend like 50% upfront work in terms of development. 50% of the time is spent on verification. So I'm using here the inbuilt verification, which is using CocoaTB, which is a nice Python framework for running verification. And we got to get this file set up, the design info, so it knows where everything is, depending on where you've installed it. And then we can run this test using Caravel CocoaTB. And one thing I learned recently, if you're an old hand and you've done this before, like me, you've typically you have to wait for about a minute or two of wall clock time for the simulation to run a few hundred milliseconds to set up the GPIOs. But if you have those user-defined set up correctly, you don't have to wait. It just you can access the chip immediately. So if we just replay that little bit. There we go. So Caravel CocoaTB, the test name is called 7seg, and I'm tagging it, so I've got the results later. And it just starts up straight away. There's this nice little tickle display that shows it's collecting the outputs from the chip and then showing what it would look like on a 7-segment. So yeah, definitely worth spending the time on the verification. Inside that, the sim directory test is test because I tagged it test. We've got waves.vcd, and we can open that with GTK Wave. So there's a ton of signals, and our project is inside mproj. And we can see the output here. Zoom out a long way. So you've got those top 11 pins all changing. And they're also accessible in the test bench, which is how that graphical display got hold of the signals. And you definitely want to make sure that the signals are visible on the outside of the chip. Don't just do verification of your design, verify that the signals get to the outside of the chip. Otherwise, when you take your bread out of the oven, it will be burnt and horrible. Then the next thing we're going to do is run full chip STA. So there's a set of 3 commands to run: make, extract parasitics. And then create the spec files, and then run the full STA. So that's what's going on here. And again, just if you've got questions, go for asking the questions. But remember also, a lot of this is already documented in the getting started videos. So Christian says, as an FPGA designer, not ASIC, if I manage to get to GDS file and submit it, is there anything I need to worry about during tape out? I think Tim is answering these for me. Thanks, Tim.
Yeah. I just said that most of the gotchas with post GDS have been, for digital design, have been covered pretty well by OpenLane.
Yeah.
Most digital designers shouldn't have to worry about problems post layout.
Yes. And yeah, just to reiterate, you want to run full chip simulations and see that you're getting waveforms coming outside of the pins. And that's, if you see that, then you're pretty much good to go. So that's finished. I should have sped that up.
Just kind of along those lines, there's some common mistakes in terms of hooking up. There's a 3-wire interface for the IOs, right? There's an input and output and an enable line, and those need to be configured correctly to propagate your signal out the pad, and simulation will obviously confirm whether that was done correctly or not. So that is a common mistake we've seen in previous designs, is where someone didn't connect those correctly. We are putting additional checks in place, which I don't know if Matt's going to cover pre-check or some of the further steps to help identify those. But that's part of the reason for doing that simulation on the chip.
Yeah.
Hey, Matt, is this a good time for the poll?
Oh, yeah, that's a perfect time for the poll. Thank you for interrupting. So, we're going to launch a poll now.
Yep.
And please fill in the information for us. It really helps us keep the webinars good and helps us to know who the customers are. And if you've got ideas for things you would like us to cover in for future webinars, then fill out question 4. What topics would you like us to cover in the future? So while you do that, we'll look at the next exciting step of the journey now that the spec has been mapped.
And if you're not familiar with these kind of terms that we're talking about, even this step, this is STAs for static timing analysis, right? So this is checking the timing of digital signaling within the chip, ensuring that the data is valid at within the appropriate clock, window for the clock. And when we talk about SPEF and extraction, it means it's looking at the final layout and final positioning, final wire lengths and widths, and kind of pulling out all the parasitic, all the parameters, all the resistor and capacitances and associated with each of those wires and those connections, and incorporating that into the analysis to ensure that all the timing is met.
And then you see this this final table here, which is checking for a variety of corners. So that's like another ASIC terminology. You want to make sure that your design is going to run at like high and low temperatures and so forth. So we have these different simulations we do. And then we get this summary saying that everything has been met. So you definitely want that to be working for your design as well before you submit it. So then we've done full chip STA. Now, the next thing we want to be doing is running the pre-check. And one of the things that has to be done to run the pre-check and get it to pass is the README has to be different to the default one. So if it's an open source project, then it's really nice to describe what your project is. But even if it's a closed source, you need to change that README. So running make precheck installs the precheck, and then we can run precheck, and that then runs the precheck. The precheck runs 16 different tests. You can tell by the way it says 12 out of 16 there. Including things like checking that the outputs have got sensible defaults. So you have to change those output, the user defines that I showed before. And I've actually hit an error here. So we've got an LVS error, and that's because I forgot to edit another file, the LVS JSON file. So that's where you just need to change the name of the gate level Verilog so that the LVS test knows what it is. So I'm going to edit that. There you go. Look, I caught myself. Didn't edit it in Vim in a terminal of VS Code this time. So inside LVS config.json, got to change that from user project example. That was the previous name. To the timer. And then we can rerun the pre-check. Tim, are you busy answering? Yeah, Tim is demolishing these questions. Thanks, Tim. That's super helpful. So this time we get all checks passed. So we're ready to add and commit all the files. So all these dots on the left-hand side are showing me all my changes. And I need to commit everything that's changed. And then I need to also add. So if you're not familiar with Git, you do need to learn a little bit of Git, how to add files to the repository. All the files that we've just created, the user proj timer files, we want to add all of them. Might fast forward this a little bit. And then I'm also running make compress because those GDS files are pretty big. Keep the repository down to a normal size. And adding the user project timer and deleting the old GDS from the user project example. Add all of those spef and spice files. And then I think we're ready to push this now to the Efabless platform. So first thing you've got to do is create a new project. So you go to platform.efabless.com and you can sign in with LinkedIn or GitHub or Google. Enjoy my profile pic there. Start a project on the shuttle you want to be involved in. That can be public or private. And then you just got to hit save. I can't have a space in the project title though, so I've got to fix that. And then we get a new repository, which is a bit like GitHub, but it lives inside efabless.com. And there's instructions here on how to now push your files to the repository. If you don't have an SSH key set up for that, you'll need to do that. That's covered in our quick start videos. And then I can push all my files there. Tim, are you answering the question about the Caravel IP for testing digital designs?
No, I'm not.
Okay, I'll take a crack at that. So I don't fully understand the question. Testing digital designs. So you're able to come up with your own tests, and we'd definitely encourage you to do that. If you want existing verification IP, that can exist for things like bus interfaces, like Wishbone bus. But if it's for your specific design, then you would also need to write your own verification IP. So I hope that answers the question. If it doesn't, then feel free to.
Yeah, I can expand on that a little bit, right? So,
Okay.
so there's a set of tests. I think you were actually touching on some of it, Matt, in your demonstration. But there is a set of verification tests that are available that we provide that for the user project examples themselves. There's also a verification test for Caravel itself that's available in the Caravel repo that you can reference and look at. And some of those verification tests include verification IP for specific interfaces like UART or SPI. So there are some slave devices. I mean, there's some devices you can connect to your design to verify the functionality of, or you can use for functional verification.
I sort of interpreted that question as how do you write your own CocoaDB test bench?
Yeah, so then I would probably look at those as examples for how to do that. There is documentation also for CocoaDB available, and let me find out. You got it?
Yeah, so this is the Caravel CocoaDB quick start guide is the place to go for that. I'll drop a link in the chat, in the webinar chat. There we go. Okay, so I pushed it here. We can see that it's pushed because it's got my new README here. Then you go up to shuttles and then choose the shuttle that you started the project on. And then that's going to take you to this, the kind of management of your project. And all of these need to be green before you can submit to a shuttle.
We're not seeing your latest screen there, Matt.
Oh, okay. Says I'm screen sharing.
I'm not seeing the Efabless webpage. There we go. I don't know. I see it.
Oh yeah. Okay. All right. So yeah, all of these jobs need to be green, and at the moment, only legal is complete because I'm always legal. And you need to get your billing. Legal is basically export compliance and stuff like that. So we're going to start off by running the pre-check and then do the tape out. The others are all super simple. So you just submit on the pre-check. You have to give it a job name. My custom is to always use the git log. So the latest commit. Because often I'm running like 10 or 15 of these as I go through, and I want to keep track of which is what. So
your window disappeared again.
Oops. There
we go.
There we go. Thanks, Jeff. Yep. So that's that job submitted, and it's now running. And now fast forward 45 minutes or so. Now that's complete. And you can take a look at the logs. You can also request the log data gets sent to you. But that's basically a rerun of the pre-check that we ran locally. One job that you can't do locally is the final tape out job. So that puts does everything, does the metal fill, runs a bunch more tests, integrates it into the Caravel pad frame, gets it all ready to be completed, basically, to be taped out. So submit that job. Now that is running. And that typically takes an hour or two. There we go, skip 2 hours, same thing. So get the logs there if you want. You can also get them emailed to you. And that's from that point on, once you've done the rest of the things, you're ready to just get your job fabricated into silicon, wait for a while for the loaf to bake, and then receive your tasty toast. So we're kind of got up to 10 minutes left now. So I'm going to hand over to Don. Feel free to keep the questions coming if there's any last things. you want to know, we'll continue to answer your questions, but I'd like to invite Don now to take over and to tell us what's coming in OpenLane 2.
Right, just a second there. Just setting up my share. Desktop 2, and yeah. So, hello everybody. I'm Mohammed Gabber from Efabless. I usually just go by Don. This is a small introduction to what we've been working on for the past year now, which is the next generation of OpenLane, also known as OpenLane 2 or OpenLane 2.0. So first of all, what is OpenLane? So OpenLane is, if in case you don't know, it's an open source ASIC flow compatible with the open source Skywater and GF PDKs that is free. So no cost, and free as in freedom and free as in free beer. It is open source, so anybody can modify it. Anybody can modify it and extend it as they see fit. Its batteries included. You don't have to go and compile your own tools or anything like that. And it is easily configurable. So with just one config file, you can get the whole flow running. It is currently the world's most popular ASIC flow, open source ASIC flow. Good correction there, with over 1,000K stars on GitHub. Right, so what is OpenLane 2? Well, it's a ground-up reimagining of OpenLane that still supports the same configuration files. It's not just a flow like OpenLane 1, rather it is a flow creation infrastructure that lets you create many different flows. And all the tools are still ready to download and run. You can so where we use Docker and for OpenLane 1, for OpenLane 2, you have 3 ways of running it. So you can either run it natively on your Linux or Mac computer using a package manager called Nix. You can still run it containerized using Docker if you prefer that, or you can just run it in your browser using Collab, and I was doing just that. So you can just run the whole thing in a Google Collab notebook. So as you can see here, I'm importing OpenLane, writing the SPM file, configuring it all just from the notebook, and I can just start doing things like synthesis and whatnot, and it all from the notebook, and without having to install anything. So the question, I guess, would be, why did we start working on OpenLane 2? Well, there are a couple of reasons. The first and foremost one is architecture. So where OpenLane 1 was monolithic, OpenLane 2 is plugin based. So OpenLane 1 is just kind of one long flow. OpenLane 2, you can actually use multiple, you can basically use plugins to add new steps to the flow or construct a custom flow entirely, and or augment the existing flows with new steps, which is obviously very useful when you're trying to implement complex chips. The other one is the data flow. So whereas OpenLane 1 just uses a global state that every single step of the flow can modify, which is accident prone, OpenLane uses a saner mode of operation where the state is explicitly captured as a data structure, and you can easily rewind, run parts of a flow, etc. So yeah, and also the environment. So whereas in OpenLane 1, there's Docker, you can only use Docker, which requires you to mount your file system with the container file system. OpenLane 2 also supports a package manager named Nix, which just lets you run the whole thing on your file system on macOS or Linux natively, and obviously you still have to use the Windows subsystem for Linux if you're on Windows. Pietro Bucella, pardon me if I butchered that. Can OpenLane be used with other PDKs, i.e. a TCMC PDK? Yes, but you will need to put in the effort to port the PDK to OpenLane 2. The explanation Matt provided used OpenLane or OpenLane 2. What would be recommended for new designs? We we still support both right now, but we do recommend OpenLane 2 at the moment. So tapeout.
Let me just qualify that a bit, Don. So I think for the current, people have asked also for like the current April shuttle and projects that are in motion right now. So currently OpenLane 2 is still in beta. So we are working on a general, we expect to be having an announcement for general kind of general use here shortly, but currently if you're doing a design for April, or for most customers, we're still recommending you use OpenLane 1.
Right, so we've had a number of tapeouts already using OpenLane 2. So Tiny Tapeout 3.5 and higher, the top level multiplexer was hardened using OpenLane 2 using custom steps, which was taped out as early as chipIgnite 2306Q. On 2309, we did harden a Caravel user project with a counterexample that was hardened using OpenLane 2. We also taped out an internal Caravel OpenFrame based SoC project where we did a custom flow that actually integrated both open source steps and proprietary steps using some of the tools we have access to, which was taped out on chipIgnite 23.11. And we've also used OpenLane 2 on the Caravel with design for tests. So that's taped in. We're still which we're planning to tape out on a future chipIgnite. So yeah, so getting started with OpenLane 2, so we've overhauled the documentation in preparation for release. So we have two brand new getting started guides. One is for newcomers and one is for those migrating from OpenLane 1. So the newcomers guide just assumes basic knowledge of digital design and takes you through hardening a design with OpenLane, and the migrants guide is for people who've already used OpenLane 1 and just need help translating the commands from, OpenLane 1 to OpenLane 2. There's also the Caravel user project for OpenLane 2, which is currently its own repo. So all you have to do is add _OL2 to the link that was shared earlier. And yeah, you can visit any of these guides. They're all live right now. And we've also worked on a full Caravel user project tutorial for OpenLane 2. So this actually takes you through implementing an accelerator for Caravel using OpenLane 2, including configuration, troubleshooting, taking design decisions, and more. And it is recommended after reading either Getting Started guide. We run into errors, we show you how to fix them. It is quite in-depth. So yeah, that's really it. We do encourage you to go ahead and try OpenLane 2 today. So we do have, I do have the link here. The repository is ready. Once again, you can just try it out in your browser if you don't feel like installing it just yet. So yeah, yeah, I believe that's it. I can take some questions right now if anybody has any.
Thanks, Don. That's great. So I know we're at the top and kind of the end of the time slot we had for this. Any last minute questions before we wrap up? Turnaround in silicon, I think as somebody's asked, generally about 4 months from tape out. So you can check the schedule on efabless.com. There's a schedule there for each of the upcoming shuttles. Next one is April. Deadline is April 24. Did I get that right? I'm guessing. No, I forgot. Sorry, let me just.
Yeah, April 24th.
April 24th, great. And then beyond that, there's a shuttle in June and September and November this year. If you're looking for help, definitely if you're ready and you want to do a project, and you sign up to reserve space on one of the upcoming shuttles, we do offer it's kind of support through design reviews and some kind of in-person or calls to help you get started and to review your project and to ensure that you've can complete successfully your submission for an upcoming shuttle. So I definitely encourage you to take advantage of that if you know you're interested in doing a project on one of the upcoming shuttles.
So Anon in chat asks, what is Jupyter Notebook? So it is a so it's basically it's a format that's popular in the machine learning and data science spaces where you can mix code and text and run it all remotely on Google servers, right? So here I have code to set up OpenLane and then use OpenLane, and you can run that just straight from your browser. So it's without needing to set it up.
Yep.
I'm gonna share the so yeah, this QR code again, if you'd like to try it out.
And we'll send these slides out, obviously, to people who registered, and we'll also do a follow-up specifically on, trying that out. For people who want to try that notebook and test it. We'll do an email out to the group or to our distribution. Turnaround time on silicon, I said, is 4 months. I think I've answered that live. There was one other comment I thought. Nope, I think we covered it. Okay, well, thanks again for everybody for participating, and look forward to seeing your senior designs, or seeing you on the next webinar.
Right.
Thank you.
Thanks, everyone.
Thanks, everyone.